This is a presentation from Winchester Academy.
Good evening, everyone. Welcome to Winchester Academy's Summer Series. We're happy you're here. I'm Anita Olson, and I'm one of the trustees of the Winchester Academy. This Thursday, there's going to be an interesting program at the Wapaka Historical Society. Ken and Barb Wardrius are presenting Door County lighthouses. It's at 6 o'clock and it's at the Holly Center. The final program is next week for this summer series. Lydia Engelbreth is presenting Wapaka Robotics, inspiring STEM in our community. This program will feature a live demonstration with a robot built by the Wapaka High School students in a competition that they were in. Tonight's hospitality person is Kate Saunders. Thank you, Kate. Please, everybody, will you silence your phones and your wristwatches, anything that makes noise during the evening. Our program tonight is sponsored by Linda and Rex Pope. Rex couldn't come, but say thank you to Linda Pope. Tonight we're going to hear from Professor Jonathan Martin, who joined the University of Wisconsin in 1994 after earning his PhD in atmospheric science at the University of Washington. He has earned recognition for his teaching, including the Under Koffler Excellence in Teaching Award, a fellowship in UW's Teaching Academy, the Mark Ingraham Distinguished Faculty Award, and the UW-Vilas Distinguished Service Professorship. He was honored by the American Meteorological Society in 2016 as the Society's recipient of the Edward Lawrence Teaching Excellence Award for outstanding teaching and mentoring that combines boundless enthusiasm with consummate skills to educate and inspire a generation of undergrads and graduate students. His research expertise is in mid-latitude weather systems. He has authored over 70 scientific papers. Pencil or computer?
Both. I write everything longhand first.
As well as a leading textbook on mid-latitude atmospheric dynamics. Jonathan regularly appears on Wisconsin Public Radio as part of the Two-Man Weather Guys segment. He served a 9-year term as chair of the Department of Atmospheric and Oceanic Sciences and was named the Princeton Review as one of the nation's top 300 professors. Tonight's program focuses on the subject of his recently published biography of an influential British meteorologist of the mid-20th century, Reginald Sutcliffe, and the invention of modern weather system science. Welcome, Jonathan.
Thank you very much, Anita. I'll just say I have a face made for radio. That is a good thing I'm not on Wisconsin Public TV. But it's a great pleasure to be with you all tonight. Thank you again for inviting me. I'm so happy to be able to tell you about some of my adventures over the last 7 years, tracing the history and doing the biographical research on this real giant in science, Reginald Sutcliffe. It's hard to overstate the revolution that all of us have lived through in the last 50 to 100 years, and that revolution is in weather forecasting. And I think it's fair to say that most of us in this room were born and lived through periods of time in our lives where a one-day forecast was effectively a joke. We didn't even talk about it as currency because it was so likely to be wrong. And yet today, despite the fact that forecasts have greatly improved and there's a residue of that long history of failure, and I hear it perhaps more than you do, but you've probably heard things like, I'd love to get paid for being wrong half the time or something like that. But nonetheless, forecast accuracy has gone through the roof. Most of us carry a cellular phone. You can look on your phone at a reasonable depiction of the weather for the next 7 days in all seasons of the year, and you can count on it being close to accurate, at least painting the complexion of the day correctly, that far out. This is unstated, unheralded probably the greatest revolution in science in the second half of the 20th century. Where did it come from? Is a really interesting question. And as it turns out, Sutcliffe was one of the pivotal thinkers to bring us all to this promised land that we now enjoy. And it's infiltrated every aspect of our lives, economic, political. You can't really find a place where it's not been influential, the ability to make a reasonable long-term and short-term forecast. So I'm really happy to be able to tell you some of the story of this tremendous thinker that I've been able to uncover over the last several years, and I'm really happy to have had the book done now, and I'm moving on to other things, but I never get tired of talking about Sutcliffe. And in order to do it effectively, I think I need to tell you a shorter story about the nature of weather forecasting before World War II, before the innovations that Reginald Sutcliffe pretty much manufactured on his own around and during the war. So let me begin by showing you this. This is a surface analysis. And what that is a collection of observations at the surface of the Earth from a variety of stations over North America at a particular time. This happens to be 7 a.m. on Victory in Europe Day, May 8, 1945. I picked it because there's a World War II theme that you'll see throughout the presentation. Now, this surface analysis has a couple of elements on it. The thinner lines are lines of constant pressure at sea level. They're called isobars. And then the thicker black lines, some of them with shark's teeth on them, in fact, all of them, except down here in Mexico, there's a little bit of that half circle, and there's one here over the west coast. These are fronts, and the application of fronts to surface analyses celebrates its 100th anniversary this year. And yet all of us have heard about weather fronts. And it's become so pervasive that in the invention for the analysis of weather systems is so powerful in its ability to convey information in shorthand that it's still used today. Before World War II, this was the primary weather map that a meteorologist had at his or her disposal, and mostly his. And the way that one would take that information to try and create a forecast was to look at the most recent prior forecast or prior analysis, extrapolate the movement of weather systems from the prior time to the current time, and then expect that the next 6 or 8 hours would see the exact same movement, and that's about all you could do to make a forecast. That doesn't account for the development of these weather systems. Do they get more intense? Do they get weaker? Does the precipitation shield change in the 6 hours? All of these things that matter to a forecast being accurate were absolutely beyond reckoning at the time. So that's why, if you have a memory of a time when forecasts were a joke, that's why we didn't have enough information. And we didn't have enough understanding of how the atmosphere works. That's not the case today. We've had a revolution occur. And I think it's fair to say that the cornerstones of where we are now, what I'd call a modern synoptic dynamic meteorology. Synoptic means simultaneous observations over a wide area, and dynamic means understanding what are the dynamics that make the weather behave the way it does, not just portraying it on a map, but actually understanding the physical dynamics that compels the weather and weather systems themselves to evolve. The cornerstones of that modern understanding are really threefold. One of them is application of a simplifying assumption to the very complicated equations of motion. That assumption is known as the quasi-geostrophic assumption. The word geostrophic refers to the fact that a large portion of the wind in the middle latitudes is determined by the spacing of those isobars on the surface map. The closer they are together, the faster the winds will be. The farther apart they are, the weaker they'll be. And the geostrophic part of the wind, which again is the largest part of the wind, will be parallel to those isobars everywhere. Imagine how important that is. This map then tells you up here in the western Great Lakes region where the successive spacing of these isobars is quite large compared to here over Oklahoma, Texas, Arkansas, the wind speeds ought to be a lot larger here. And they'll be parallel to these lines. They'll be coming from the north and then from the northwest as you get to Madison. Here they'll just be kind of light zephyrs. So that's a powerful assumption. Applying that assumption to the much more complicated equations that describe the motions of atmospheric particles allows us to facilitate physical insight. This was a brand new development. Adoption of pressure as the way to think about the vertical direction in the atmosphere, as opposed to what might occur to us more naturally, height. The higher you climb, the higher you are. You might say that's the best way to look at the vertical direction. It's not, as it turns out. The best way to look at it is in terms of pressure decreasing as you increase your elevation. So using pressure as a vertical coordinate is a big advantage. And then developing an equation that tells you something about other measurable variables that can be concocted in such a way that you'll get information about how the air is moving in that vertical direction. Is it going up? If it's going up, it's cooling by expansion. Cloud and precipitation development is then encouraged. If it's sinking, it's being compressed as it moves to higher pressure and drying out. So you really need to know that. What direction is the air moving in the vertical direction? All three of these cornerstones, though there were other smart people working on problems related to them, Sutcliffe was the pioneer in all three of these. And I hope to convey to you in the talk tonight that he did it pretty much in isolation, which is just remarkable, just remarkable. So who is this guy? Where does he come from? What's his background? He was born on the 16th of November 1904 in Wrexham, North Wales. That's at the little red star. This was one of those rare autumn fair and windless days in Wales, apparently, but that's of no concern. Nonetheless, this is a weather map from the day he was born. He was born in this home at 88 Bradley Road in Wrexham. I was there in I guess it was March of 2015. I did not have the guts to knock on the door, but perhaps now someone's read the book and found out that they live in the home of a famous person and didn't know it beforehand. His family is pictured here in the mid-1920s. His father, Ormerod, and his mother, Jessie, were from Hebden Bridge in Yorkshire. And they had a family of 4 boys. Their oldest, William, died in 1906. I think it was scarlet fever. And then Robert came along, and then Reggie was the 3rd child, and then the youngest brother was Alfred, and that's the picture of them in the mid-1920s. Ormerod worked in the Wrexham Cooperative. He was a grocer. And he'd spent a number of years. Reggie Sutcliffe was the first in his family, the first generation in his family to not work in factories as a child. His father did and his mother did. And so, but his father graduated to working in the cooperative movement, which was actually a rebellion against the real disasters of the industrial age in England when it was first getting on its feet. But he couldn't speak Welsh, and that doesn't put him in minority. Most people can't. It's a very hard language to learn, apparently. And so he had trouble doing business there, and they decided that once the kids were born, they wanted to move back to Yorkshire, and they moved to the town of Cleckheaton. Here's the town hall of Cleckheaton. And they moved to this exact replica of a row house at 9 Prospect Terrace, Cleckheaton. Again, I was at the doorstep but didn't knock on the door. Someone was home this time, though. There's a car there. But I didn't do it. But the same applies. That's where Sutcliffe grew up. And if you walk to the end of Prospect Terrace and look to your left, there's a slight grade, and up about a half a mile from that grade, there's the road itself. That's Whitcliffe Road. And if you go up about half a mile, you get to the crest of a shallow hill, and there's this beautiful school. This building is no longer on the campus of the Whitcliffe Mount Grammar School. It was just demolished in July of 2017, but I got to see it before it was. And this school opened in 1910, and it was conceived in controversy. At the time, Cleckheaton and several other towns in the Spen River Valley of the West Riding of Yorkshire were growing at a fairly remarkable rate, and none of the towns were big enough to be the 800-pound gorilla that would determine where the new schools and new facilities would be built. So they had to kind of work this out among the different municipalities. And the first plan around 1908 about expansion of facilities was going to put a new school in the neighboring town of Heckman-Dwike. That's the name of it, pretty amazing name. And that would have required a 12-mile round-trip commute for every kid from Cleckheaton every day, Monday through Friday. And the people of the town were not happy about that. And as it turns out, in a really great demonstration of noblesse oblige, some rich industrialists who lived in Cleckheaton decided, let's not let this happen. They decided to raise the money to build their own school by subscription. And most of the donations came from the rich people. A few one-pound notes came in from the families who would actually end up sending their kids to this school. Just an amazing history to this school. And in order to make this plan work, they not only needed to get buy-in from the community, but then they had to persuade the municipal authorities to let them do it. The second part wasn't so difficult once they'd raised the money, which didn't take that long. But in order to galvanize support for it, they had a series of meetings in the town where they would kind of rally citizens around the cause. And one particular one I have to just highlight to you. This was a speech delivered by a gentleman named Reginald Grills, who was one of the so-called Cleckheaton conspirators. They were immediately dubbed as radicals for wanting to do this for their own town. He held a meeting on a Sunday, April 12, 1908, in his own home, and this is what he said. We live now under a democratic form of government, when everybody has a vote, and it stands to reason that if the power to rule is given to many, while the faculty of reason belongs to the few, the government is not a democracy at all, but government by the mob, something with which we unfortunately have some experience. If we want to have a perfect system of democratic government, we must have an enlightened people. And were that the only reason for a complete and universal system of education, that in itself would be sufficient to justify every effort that's being made in improving our education. They succeeded. This is a statement that resonated with me. I read this in the spring of 2014 when our then governor was attempting to do as much damage as he could possibly do to the University of Wisconsin. So this really hit me hard. And this was what have we learned in 100 years was the question I had in my mind. Wycliffe Mount was a great influence on Sutcliffe's life. He started there in September of 1916. This is a picture of the staff in 1920. I'm highlighting two of the people who had a particularly profound influence on him. The headmaster, Herbert Claiborne, is pictured in the middle. And then his science master, William Pearson, who served in World War I, won the Iron Cross, and then, or the Victoria Cross, and then he came back and taught at the school. They were big influences on him. Sutcliffe himself was a big man on campus. He was captain of the soccer team. There he is, almost Tom Brady-esque in the back row. This is the 1921-22 squad. They were below 500, but they proudly competed, apparently. He was also the captain of the cricket squad, and he ran track and he swam. So he was a big athlete. He was the head boy, which is the top male prefect in the school. So this is a person who had a gregarious nature to him, made friends easily, and gained influence by doing that. So that's a great picture of Sutcliffe. All of these pictures were saved from literally from the trash heap by the current learning resource manager at the school. When I went to visit them in 2014, I'd been contacting people by email, of course, and Amanda Raby's her name. She told me when I got to the school on the day that I visited, all of these pictures and various notebooks and various logbooks from the school's history were being thrown out one afternoon. She didn't know what they were. She went to her car and looked at the dumpster and saw all these cardboard boxes, and she said, "What's that?" So her curiosity piqued. She went over and looked in, and there's all these famous, all these old photographs and various records. She went back and forth 4 or 5 times that day to save it all. And that's the only reason that archive exists. And I was the beneficiary of it. So I sent them a copy of the book as soon as it came out. And they got it in their library. And so when the pandemic's finally over, I'm going to go over and give a talk to the secondary schoolers. So there's Sutcliffe as a football player. He was a sports champion in the school. He graduated in 1922. This is look at that medal. It's 100 years old now. His daughter Ellen showed me all these things. Isn't that great? When he graduated in 1922, his family was lower middle class. His dad was a grocer. His mother didn't work. And he didn't have money to send him to school. But he did well in school, of course, as you might guess. And he won what was then known as a county major scholarship, which paid for tuition at the local university, which was University of Leeds. No bad school. And so he started at Leeds in 1922. And what a campus. It's got all manner of different buildings on it. This is like the Harry Potter portion of the campus. But then it has brutalist architecture, just like our humanities building on my campus. In fact, there's more brutalist buildings on the University of Leeds campus than anywhere else in the world, as it turns out. So it's really a wild place. And so he started there in 1922, and he took a mathematics course. He had taken the science curriculum at Wycliffe Mount, which did not include study of Latin. And if you didn't study Latin in the 20s, or maybe for decades after that, you didn't get to even think about Cambridge or Oxford in England. And he was smart enough probably to have gone to either of those places, but he didn't know Latin. What a shame. Right. So there he was in 1922, taking math course. He did very well, and since it only covered tuition, he didn't get to live on campus. And so he didn't really have much of a collegiate experience. Not till his 3rd year did he actually start to do some things that would take extracurricular time. And one of those was swimming. So there he is on the far right, smiling gaily as a member of the University of Leeds swim club. He also was president of the Mathematics Society that year, and as a result, he got to give his first ever after-dinner speech, something he became very famous for later in his life. So that was his first time ever. I couldn't find any records of the Mathematics Club. I wrote to them. I don't know if these Generation Zs or whatever they are. They don't care about some of this stuff, so they just didn't look it up for me. And when I was on the campus, I couldn't find anybody who could help me. So I wish I could have found that. They might have had a record of it. Anyway, he graduated in 1925 with his degree. It had not been satisfying to him as a student. He was, in his own testimony that he had in some interviews later on in his life, he said, well, it was just a battery of exams and you didn't really learn anything new. There was no challenge to be creative. But the university really had their eye on him. They said, you've done really well. We'd like to keep you on as a graduate student in mathematics. Oh, would you? Yeah, but we can't give you any support. So his family didn't have money. There was no more county major scholarship money. He really was at wit's end with this wonderful opportunity, but no way to finance it. Whitcliffe Mount School comes to the rescue again. His science master and his headmaster, Claiborne and Pearson, both said to him, I think he went to Pearson first in his recollection, he said, Pearson said, well, don't forget, Reggie, you didn't use the endowed scholarships from the school to go to Leeds. So maybe you can make the case to the board of directors that you'll be the first PhD ever to graduate from Whitcliffe Mount, and you never took any money from their endowed scholarships. Let's see if it works. So he applied for the Alfred Law Scholarship in 1925, and they said, again, in a demonstration of don't play by the rules strictly, do the smart thing, they said, sure, let's do that. Let's get you to the University of Leeds for your PhD. That'll be a great mark for our school. So that's how he got to go. And the scholarship did include money for him to live there. So he finally got a chance to well, not quite yet. That's not true. He started graduate school living at home, still in Cleckheaton. And he went to work for Professor Berwick, who was a number theorist and an algebraist. And Berwick had, unfortunately, a short career. It appears that he died of ALS in the mid-1940s. He stopped going to work in 1941 and then died 3 years later. And they talk about it with all of the symptoms of ALS. But Sutcliffe hit him at the productive peak of his career. And apparently, this guy was a real sage in terms of how to mentor students. Because Sutcliffe, arriving from a disappointing undergraduate experience in math, not being sure what he's going to do as a graduate student, which will require research. How do you do research if you've never even been challenged to be creative? It really was bothering him. And he said this later on in his career. I always will remember Berwick's introductory talk with me in which he relaxed that tension that I had by saying, don't worry too much about your research at this stage. The important thing is to start doing something. And I'll tell you something, maybe many of you can agree. I think in almost no matter what walk of life you work, and I can certainly testify for it for myself, even when you know what you're doing as a research scientist and you're done with a project, you better start doing something. Because if you're sitting back and looking backwards and saying, I'm really proud of what I just did, you're sunk. If you're looking forward and so challenged that you don't want to start anything, you're sunk. You've got to do something. And I thought that was great advice. So this was a great collaboration that Sutcliffe had with Berwick. But less than a year into it, Berwick was highly recruited by the University College of North Wales, and he was enticed to go back there as the chief of their mathematics program. He writes this letter to the registrar in May of 1926. Consequently, it will be necessary for me to resign my appointment at the University of Leeds beginning 30 September 1926. Thank you for everything you've done for me, and so on. So Sutcliffe is scurrying to figure out what's he going to do. He's only 9 months into his PhD with this guy. How is this going to work? He's writing the registrar, he's talking to all his colleagues, and so on. It turns out they end up saying, why don't you follow him to Wales? When you're done with your degree, we'll award it from the University of Leeds. That's how we'll work this out. So that's what he did. Sutcliffe left home for the first time in his life and moved into this house at 37 Upper Garth Road in Bangor, Wales. And you might be able to see the ocean here. That's the little bit of ocean between mainland Wales and the Isle of Anglesey, because that's right where this town is, right on the end of the mainland Wales. So Sutcliffe's living away from home for the first time in his life. And he's, what is he now, 22. So the first time he's ever lived away from home, he meets a young lady who's from neighboring Henry Palkin, which is about 40 miles to the southeast. This is Evelyn Williams, and she's from a Calvinist Methodist family, and her older sister, who's older by about 12 years, had studied languages at University College North Wales, so that's what Evelyn decided she wanted to do. She was in her first year when Reggie showed up as a graduate student, and he was instantly smitten with her, and she was, of course, indifferent. In fact, her daughters tell me that she was interested in some local rugby tough guy. They don't really know more than that, but that's kind of interesting. But Sutcliffe was persistent, and unfortunately the details of that persistence are now lost, but they were a perfect match. She was a very athletic, very intelligent, very progressive young woman. She was interested in a lot of different things. Her interest in various things never atrophied, And they had a wonderful life together. I'm giving away a little bit of the story there, but that's one of the earliest pictures that her family had of them together. By June of 1927, Sutcliffe finishes his PhD dissertation. I'm one of about 6 people in the history of the world to have seen this document. His daughter Jenny, who lives in France, had it somehow, and his older daughter didn't. It's really interesting how he parceled out these things to his kids with not much obvious planning there or strategy. But look at the title of this thing. I got to get around to it. I can read it. Interpolation and tabulation of the numerical values of functions of a complex variable with a digression on certain subgroups of the modular group and the functions associated with them. What? This is about 100 pages long, and there's some beautiful color diagrams. All of it was handcrafted by him, so he did the whole thing. And I've given a talk with this slide in it in front of math departments, and they don't know what the title means. So pretty amazing stuff. And of course, then there were reviewer comments. And they're fairly voluminous. I'm showing you just a little piece of those reviewer comments, but it's interesting to me. I left the title visible on purpose because in the midst of this pages and pages of reviewer comments on this thesis, none of the reviewers suggested, Reg, why don't you shorten the title a little bit? So how do you do that? But what's going on here? Look, in all of this, the work, there's nothing that's neither difficult nor novel. So that's that's not very good praise. But listen to this. But the author goes on with a practical aim in view, and you can read some more of this, and you say, he formulates formula, which are undoubtedly of practical value. So there's something here that is characteristic of Sutcliffe's work through the rest of his life. Every problem he approaches, he thinks about it from a practical point of view. How can I make the greatest advance on an important problem that's also at the same time practical? And what could be more important if you're finding yourself into meteorology, as you'll see in a minute, in the late 1920s when all you have is surface weather maps, making something practical that's better than that. And that's his whole career. So it started when he was a PhD student. His advisor Berwick said, this makes a useful addition to a theory initiated by Klein on which I hope Sutcliffe will work again. He never did anything in applied math ever again. And the reason is, he was getting fairly serious with Evelyn, and he needed a job. He didn't want to be a schoolmaster, even though he had great respect for those who had been in his path. And he knew that they enjoyed a life of respect in their communities. He didn't want to do that. But as amazing as it sounds today, less than 100 years later, if you get your PhD in mathematics today, you can write your ticket. You go anywhere you want for any salary you want, just about. Not then. So there weren't a lot of options. There was a primitive placement office at the University of Leeds when he came to turn in his document, I guess in early June. And he was, of course, friendly with the person in the office. He's one of those people, I think. And she suggested to him, hey, Reggie, don't neglect the meteorological office. They often hire PhDs in mathematics. And it turns out, he called them up and got an interview, but it turns out that they would hire PhD mathematicians who had absolutely no other options because they were usually the people who were sort of on the lower end of the stick, because it wasn't considered to be a job of any sort of prestige to work in the meteorological office. But he was desperate. He needed to get himself employed. So he called them up, and they scheduled an interview with him on Monday, September 5th, 1927, in this building. This is now a building, a science museum on the campus of Imperial College in London. It's at the Kensington station. There's like a 1-mile corridor you got to walk at that station if you've ever been there, and then you get to this place. But anyway, it's pretty cool. He went in there and had his interview. It took about 5 minutes by his recollection. In September is still the end of summer vacations. He was interviewed by David Brunt, who later became Sir David Brunt, a famous meteorologist later in his career. And Brunt must have been told, if this guy doesn't strike you as a complete disaster interpersonally, hire him. Because it was a 5-minute interview. And then he started his career at the Met Office. This is the cat scratching the post, if you ask me. Starting somebody on a Friday, why do you do that? You're just telling them who's the boss. But anyway, Friday, September 30th, 1927. And then he had an almost 45-year career with the Met Office, and it was, as you'll see, distinguished. So that's how he started. What did he do when he was there? Well, he was working in the first year or so at compiling statistics for air and ocean routes across the Mediterranean for the Met Office. They were really, of course, interested in that. Mussolini had been in power for 5 years by this time. Italy had the largest submarine fleet in the world in the late 1920s. And the British had a lot of possessions and interests in the Mediterranean. So they wanted to make sure that they knew the weather and ocean currents and how the two interacted on the Mediterranean so they could come to the aid of any of their possessions on the double. A year into his work on this job, he was sent to the outstation at Malta, populated by 5 scientists. That's it, really small. And Malta had only been brought into the Commonwealth of Nations in the last 5 years. So that's where he went next. I don't think he minded. A lot of people in the Met Office with families in the country didn't want to move there, but he was unaffiliated at the time, and so he said, why not? I'll give it a try. As luck would have it, arriving there in late November 1928, this was just weeks after the evangelist of the Norwegian School of Meteorology, Tor Bergeron, had arrived there at the invitation of the British Met Office to see whether or not the Norwegian analysis techniques, which includes frontal analysis that I mentioned earlier, would be of any value at all in forecasting weather in the Mediterranean. The Norwegian school introduced the notion of frontal analysis right after World War I. And in fact, they stole the word front. They appropriated it from the headlines of the war. They knew everybody would know what a front is. It's a battle line between, in this case, opposing air masses. And in the newspaper case, opposing armies. Bergeron was the disciple of the zealot of the Norwegian school model, and he went all over the world. He ended up marrying a Russian woman because he was in Moscow for 7 or 8 months. And then he comes down to Malta. And it's interesting that it took 10 years for the British to decide that what they called Viking science was worth a look. That's really interesting. That's what they called it. So Sutcliffe is a year into his job at the Met Office. It's not that exciting. Maybe there was some cynicism in his character. I can't tell. His daughters don't testify to that. But this is the second time that you get the impression he was not interested in what was going on in his mathematics degree and then in the Met Office. But who can blame him? He was doing boring statistical work on air routes. And Bergeron comes along and shows him and his staff members at Malta how to really draw a beautiful surface map, how to take data that doesn't have a voice and make it speak, make it sing, actually, in harmony. How do you make sense of the weather? You do it by expert analysis and employing expert judgment on how to make sense of those observations. Bergeron was peerless at that. This gave Sutcliffe a much-needed shot of intellectual adrenaline. He was suddenly reinterested in weather systems and meteorology more broadly. He had no prior experience before he had this job in meteorology. Bergeron resurrected his life from life support. That is really important, as it turns out. The next spring, Evelyn finds her way down to Sliema, Malta. 20-year-old Welsh girl, okay, from a Calvinist Methodist family. They're not particularly conservative, certainly not socially conservative, but nonetheless, I don't think her dad was thrilled to say, yeah, just find your way. They must have figured out how to get her down there with a Royal Air Force wife or Royal Navy wife or husband or something like that. Anyway, he's down there Tuesday, March 29th, 1929. They're married. That's their wedding picture. Fantastic that that's still available. And Sutcliffe is beginning to dabble in research work as a meteorologist. And it's interesting because at the Met Office, there was an official prohibition against doing research work during the workday. They figured they couldn't justify it to, His or Her Majesty. And yet at the same time, it was well known that if you did original research work, you would catch the attention of the higher-ups and put yourself in better position for promotion. So Sutcliffe played the game and did this work, I guess, on his off time. He started thinking about very simple problems and publishing them in very low-profile publications. The Meteorological Magazine is one of them. This is a professional note that stayed in the meteorological office, talking about autumnal gravity wave phenomena in Malta. They didn't talk about them in those terms, but that's what they were. Rainfall at Malta comes in big clumps, and so how do you make long-term forecasts in a place like that? Is there even any value in trying to make long-term forecasts? Questions that he posed in very short, as I say, low-profile examples of research. But he was beginning to emerge, from the soil as a force. And there you can see the last one's dated October 1932, and that's about the time that he left Malta. So he was there for almost 3.5 years, and then he and Evelyn came back, and the next duty station was Felixstowe on the southeast coast of England. And they played golf and tennis and a variety of other things there, and probably playing golf, it got him thinking about the sea breeze, which is a kind of a daily occurrence there at Felixstowe. And he wrote a paper on the sea breeze. This is just a surface analysis that I had in here for reasons that I guess I wanted to emphasize. And now I remember why. So he's working on the sea breeze because that's a proximate problem. But, it's a little bit more technical, not of great interest. he was thinking all the time about how do these weather systems develop and decay? How do anticyclones, regions of high pressure, develop and decay? So this long-standing unsolved problem in meteorology manifest in these surface analyses. Here's a region of low pressure. Here's several regions of high pressure and so on. They have life cycles, but what controls their development and their decay? And as I say, this was not a well-known problem. And the use of such surface maps was a tool in forecasting, but it didn't provide an understanding of these weather systems. And he really wanted to do that as he was beginning to emerge as a research scientist in the early 1930s. Now, despite the fact that these maps didn't provide much insight about how the weather systems work, the meteorologist did know some things about these weather systems. For instance, here's a picture that depicts a surface isobar, just one, in the region of, the L is the region of low pressure, and then this is a level some 3 miles or 5.5 kilometers above the ground. They did know that because there's friction near the ground, that some fraction of the wind at the surface is going to cut across the isobars directed from higher to lower pressure. So it's going to look like that. And that wind is going to converge at the center of that region of low pressure. It can't, upon converging, bury itself in the ground or you don't make a pile of air any more than you make a pile of water, right? Fluids don't do that. So when they come together at one spot, they rise if there's a solid boundary underneath them. And the rising of that air that converges is going to force the air to lower and lower pressures because the pressure decreases the higher up you go. And that means it's going to expand into a lower pressure environment. And the expansion doesn't come for nothing. You've got to pay a price to do that expansion against the environment. The price is the temperature of the air parcel goes down. And when the temperature of the air parcel that's been lifted goes down, it's going to encourage condensation of invisible water vapor and turn that into clouds and precipitation particles. Not only that, at some level above the surface, that air that's risen is going to diverge out the top of that column that I've colored in green. So there's going to be a net evacuation of mass from that column of air. It's rising and then it's diverged and placed somewhere else. So that column, every second that goes by, if it has vertical motion like that, is going to weigh less and less. And what does that do to the surface pressure? It lowers it. So he's thinking, how do I quantify this divergence, convergence stuff and figure out how the pressure at the bottom of the column will respond to an imbalance between these two things? And all the while, the rising air tells me where I should expect clouds and precipitation. So imagine how exciting this was to start thinking about, I know what the pieces on the chessboard are, but I don't know how they're related yet. That's a great place to be on a research problem. And this is going to take decades to solve. The same opposite set of circumstances occurs for a region of high pressure, just to fill in the gaps. There's a region of high pressure. The air diverges away from that. Again, following the same rule, the air is going from high to low pressure under the influence of friction. Some fraction of it has to cross the isobars. That fraction I'm coloring in red is the non-geostrophic part of the flow. We call it the ageistrophic wind. Now, if that's happening, the air has to be sinking. It hits the ground, and that's why it spreads out. And if the air is sinking, it's moving to higher pressures and getting compressed and warmed up. And the relative humidity goes down. You're going to lose your clouds in that case. And the air has to converge somewhere above in order to force that column of air to sink. And you're stuffing air in at the top, probably at a faster rate than it's able to escape at the bottom. So the total amount of air that's in that column gradually gets larger and larger. What happens to the pressure at the bottom of that? Goes up, because there's more mass there. Oh, tantalizing, but not yet solvable, right? Oh, man. So he writes his sea breeze paper, all the while developments in the back of his head, and the sea breeze paper gets read by somebody else. And he published it in a high-profile journal, one of the highest-profile journals in the world, still, the Quarterly Journal of the Royal Meteorological Society. And in the old days, you'd read your paper before the assembled Royal Society. And he didn't get to do that because he was deployed to Alexandria during the Abyssinian crisis as a forecaster for the British fleet. They amassed the largest naval group since the end of World War I to combat Mussolini rattling his saber against the overpowering foe of Ethiopia. During Christmas time of 1935, Sutcliffe, during this tour, finds himself in Nazareth. He's not a religious person, but he finds himself in Nazareth, and he has this rosewood Bible that he bought for his, well, look at the inscription, to Ellen, from her daddy in Nazareth. Look at this curious word, for February 19th, 1936. He bought it in anticipation of his daughter's birth. He didn't know when she was coming at the time that he bought it. She had this thing for her whole life and didn't understand. I asked her when I first saw it, this is beautiful, how come he was in Nazareth in 1935? The obvious first question. John, I have no idea. I figured this out for her. So a family heirloom was explained by my curiosity about his life, which I feel great about. So that was really exciting. You know, this whole journey for me has been populated by a whole bunch of such episodes where you just have this life-changing feel that you're involved in something much larger than yourself. This was one of the primary examples of that. He comes back from Abyssinia, or from the Alexandria, in the spring of 1936, and he starts working on testing and teaching pilots, both Royal Air Force pilots and private pilots, about basic meteorology, because that's part of their qualification process. And after a year or so this goes by, he complains to the director of the Met Office that, you know, there's no basic syllabus and there's no textbook by which we can do this more effectively. And the director thinks about it, I don't know for how long, but probably not long, and he says, you know what, I think we need to do that. You've got a good idea. We should have somebody write a book and figure out a nice syllabus. And Reggie, you are the person to do it. He was surprised. He thought, what? I didn't expect that was going to be the answer. What's more, the director said, and I don't think the office environment is a very good place for you to do this important work, so you can have a 6-month leave. You can work at home for 6 months. On the southwest coast of England, at this time they were in, I forget the name of the town, but anyway, dream come true for a Brit to live on the southwest coast. And Ellen's about a year old. He's going to get her first words, which are in Welsh, while living at home, which is really cool. And he writes this book, Meteorology for Aviators. This is Sutcliffe's first chance to do any really serious reading in the science of meteorology. I'll remind you again, he did not have a background in meteorology when he started with the Met Office. So this was his chance to read in French and German what was going on in the science, and in English as well. First time he really got to educate himself about the science. And the book came out in 1939, and it was a huge hit. I'm sure it was translated into French and one other language, but it's not German. But I'm sure it was on the shelves of Luftwaffe pilots. There's almost no question that was the case during the war. Because the name Sutcliffe is synonymous with meteorology when this book comes out. So having just read for the first time in the science, put down some of his thoughts, the biggest chapter in the book is about development and how it's an unsolved problem. So I'm not guessing when I tell you that. He was really thinking about that. He starts to write some interesting papers with colleagues because he's now a little more educated. First one in his Annus Mirabilis, like they talk about with Einstein, 1938 to 1939, is this one with Charles Durst and Sutcliffe, 1938. They're going to discuss the problem of the mechanism of eviction of air from what they called tropical revolving storms, hurricanes. And they're going to do it by examining the equations of motion, not by some other sort of hand-wavy thing. They're going to get right into the mathematics and try and figure this out. Here is the example of the kind of language that filled the meteorological literature before these kinds of innovations were made. If vertical motion occurs in the atmosphere in a region of horizontal temperature gradient, then ascending motion gives a component of wind from warm to cold, and descending motion a component from cold to warm. What? That gives you a headache just reading it. And when you're tasked with making sense of it, you've got to read it several times and take out a pencil and start drawing pictures. It still doesn't help. So they attacked it by mathematics. The ageistrophic part of the wind can be related to the acceleration of the wind. Oh boy, that doesn't sound easy. And you got to do a little mathematical operation on it. You can change the expression for the acceleration into the sum of 3 different terms. It gets worse. And they focused on just this one, which I'll tell you what it means. It's the vertical motion times the vertical shear of the wind. How's the wind speed and direction changing with height? So the z is the vertical direction. Now, they make the innovation of saying, it's hopeless to do anything with this term unless you assume that the vertical shear can be related to the horizontal temperature contrast by the geostrophic relationship. Okay? Now, I know this is not particularly up your alley, but I have to show you the complication and the creativity that went into skinning this cat. Okay? So that's what you get for the dV/dz part, 1 over f times t, k cross del t. And that means you got to do this part outside of it. So k cross, blah, 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 blah. But when you do the whole thing, the x direction part of this ageistrophic wind, the wind that will evict air out of the tropical cyclone, is directly related to the horizontal temperature contrast and the sign of the vertical motion. So you draw a careful picture. Here's the picture. Let's say in yellow, the air is rising. So W has a value that's positive. And notice that the temperature gets larger, goes from cold to warm as you move in the positive x direction. That means this thing, this temperature change in the x direction, is also positive. Everything's positive except the minus sign. So that means that the x direction component of the evicting wind is going to have to go in the negative x direction, from warm to cold. And the warm is the eye of the hurricane. So the air is getting kicked out of the eye of the hurricane under these circumstances. They were thrilled that they'd use the equations of motion, and they're not uncomplicated, to come to this rigorous conclusion. The problem is you can't make the geostrophic assumption for tropical cyclones. But who cares? They made it. They made it. They made something happen. The next paper is Sutcliffe on his own, 1939. And he does effectively the same thing. He takes those same terms and he says, Durst and Sutcliffe were the only ones to ever pay attention to these. Let's just assume that the flow is quasi-geostrophic. And he'd already done that before, but no one had ever used this term in a paper before Sutcliffe, 1938. And this is the first English language invocation of this incredibly powerful simplifying assumption. He did it. Meteorology for Aviators comes out in 1939. As I mentioned before, the name Sutcliffe becomes synonymous with meteorology. It's a tremendous next contribution all by himself, 1939, cyclonic and anticyclonic development. Nearly a decade of thinking about development. What can we say about it? Well, he starts out with the same thing. I'm going to go through this quickly. I don't care if you pay any attention to it. K over F across the acceleration tells me about the important ageistrophic part of the wind, the part that creates the divergence and the convergence. It's not uncomplicated, but you can say the wind at the top of the column is the sum of wind at the bottom and the wind at the top, and that allows you to end up with this interesting relationship. The difference in the accelerations, which will give you something about the difference in the ageistrophic winds, eventually is forced by two terms. The first one is really ugly. There's a huge long expression. If you're careful, you can draw a picture that eliminates most of the terms. And you're not violating the mathematics by doing so. So draw a picture like this. I tell my students, don't get nervous about this. Figure out a way to get around it. Draw your isotherms, which will tell you the direction of the shear vector, US and VS, in one direction, all along the y-axis. And then put your surface isobars there, and these gray arrows represent winds. And you're going to, from them, be able to determine derivatives of the winds in this picture. Well, if your isotherms are all in the y direction, then there's no such thing as a y direction temperature contrast, so there can't be any vertical shear in the x direction. Those two terms go out. And there's not going to, at the center of the low, there's not going to be any such thing as a dv naught, that is y direction wind derivative in the y direction. So that term's going to go out. This whole ugly thing turns out to be just that, for that picture. And you can manipulate that and end up convincing yourself that the cyclone is going to see net column divergence to its north in this picture, net column convergence to its south. So where is the low pressure going to move? It's going to move where the air is being evicted, to the D. So you know where the cyclone's going to move. And it's rigorous. It's not a guess. And then you can take the other term, which isn't quite as ugly. This is just how does the shear vector change? Well, the shear vector depends on how closely spaced these red lines are. And it's going to be parallel to them with cold air to its left. If you push them closer together, which you might do if you have that wind field on top, you're going to make the shear vector longer in the positive y direction. And when you do that, well, that means that your ageistrophic wind is going to be diverging on the warm side, converging on the cold side. This is why fronts have a circulation where the warm air rises and the cold air sinks. And Sutcliffe discovered this. I'm putting my notes together for my first class ever at the University of Wisconsin. Someone asked me this at dinner. And I realized Sutcliffe's got his fingerprints on the franchise about weather systems. Everything we know about them, he figured out. And nobody knows about him. Even in my own science. I have colleagues around the country teaching weather systems to their students, and they hardly mention Reginald Sutcliffe. This is a horror to me. Okay, so I had to do something about it. And part of that something is talking to you. So I know this is complicated. It's the last time we see any math, but I wanted to show you that this is, you have to be creative. You're playing within really confined rules, like a musician. Musician can't put any notes he or she wants together. There's rules that make that work. And yet creativity abounds. And the same thing here. But it's a bittersweet year. September 1st, Germany invades Poland. Here's Sutcliffe's conscription papers. His career is at its peak. He is the synoptic dynamic meteorologist in the world, making all of these brand new insights on his own. And then the war comes. You know, Ted Williams, Joe DiMaggio, Bob Feller, they all sacrificed prime years of their career to World War II. That was not the only place where that happened. Here's another example, and there's many more, I'm sure. Look at this conscription paper. Imagine having your hands on this. It's unbelievable. Tenable for the duration of hostilities, initiated October 1939. So Sutcliffe is first sent to Arras in northern France during the phony war. Nothing's happening. They're trying to set up a meteorological forecasting unit there, but they don't have good equipment, and there's not anything really, there's no urgency to making good forecasts, so it doesn't matter too much. Then the Germans invade the Low Countries in the early spring of 1940, and they make, of course, their famous rapid progress to the coast. They're evacuated to Boulogne first from Arras. They thought 70 miles to the west, we'll be safe. And then 2 days later, the Germans are right there at Boulogne. And then he's evacuated to Dover in late May 1940. But then he's deployed over the front, south of Paris, to Orleans, to lead the forecasting effort for an operation known as Haddock Force. And they're going to go down to southern France and bomb the industrial towns of Milan and Turin in northern Italy. And the French are all on board when everybody's making their way down to Salon. But as soon as they get there, well, wait a minute. The French say, non, we can't have you doing that. And so they eventually have to, they drive down by the 7th. They got to evacuate about 10 days later on a collier from Marseille to Gibraltar. And this is days around the capitulation, of course. They're in Gibraltar. And then in June 24th, I think the BBC broadcasts at home, if you have a British serviceman over in France, you can forget about seeing them until this thing's all over, because they're either in prison or they're deceased. Okay. Horrible. Imagine, Evelyn's up in Oxford with her sister, with Ellen, hearing this news, and they haven't heard from him. So they don't know what's going on. He's on a ship evacuating from Gibraltar to Liverpool during that exact same time. They don't know that. He gets to Liverpool on July 1st, and he sends this telegram, 9 words. Just arrived, feeling grand, see you soon, love Reggie. How do I have access to this? Ellen has it in a frame in her house. 75 years after it happened, she couldn't let this thing fade away. She told me that she could remember as a 4.5-year-old, even all those years later, the weight of the world lifting in the house. She saw her mother and her aunt, hugging in the vestibule, and she didn't really know what was going on, but they were both crying and laughing and so on, and she said it just felt light. It's amazing. So that's what happened there. So then Sutcliffe comes back. He has a week off, thanks Admiralty, and he's sent to Exning, Newmarket, where for 3.5 years he is the chief forecaster for No. 3 Bomber Group. And the whole family lives together. His daughter, Jenny, is born in 1943. So they get to spend, unlike a lot of service people during the war, they got to spend most of the war together. And so that was a great blessing. He is doing some great work. He's mentioned in dispatches 3 times during the war. This is a big deal. And this is for work on flight level winds. He's made a member of the OBE, Order of the British Empire, on January 1st, 1942. And here's Ellen and Evelyn at the induction 6 months later, early July 1942. And Ellen says this whole sky was filled with those mini blimps that were sort of aircraft interference stuff. She remembers that still. And then he's working like crazy on trying to figure out how can I make better forecasts for flight level winds. He had nightmares about the war for the rest of his life, sending his own comrades out to die, and then knowing that they were doing really serious damage to civilians in parts of Germany. But nonetheless, the job was to safely get people out and safely back, and so you had to forecast upper level winds. The best way to do it, he started to discover in his job, was to use pressure as the vertical coordinate, because it gives you all sorts of advantages. He ended up working with a colleague, Otto Godard, a Belgian mathematician, for a couple of years, and they built a whole analysis scheme on the idea that the height of a given pressure surface above the surface is a function of just the temperature in the column that underlies it. That's all you need to know. average temperature, and you can tell how high that surface is. And if you can do that with a reasonable accuracy, you can build some pretty good forecasts of the winds. So here's a surface analysis to illustrate this point. Those are isobars at the surface. And you can get a new one of these every 3 to 6 hours. Even during the war, that was possible. And then if you could supplement that with a few stray observations, flight level winds perhaps, maybe even a radiosonde sent up by the resistance over the continent, you'd get some information about the vertical structure of the temperature. That will tell you how high the next isobaric surface might be. And you can start to construct, those red lines will give you some idea of the relationship of various heights, and that will give you an ability to build an analysis at a level at which you have no direct observations, and yet it's pretty accurate. So they're making great forecast upper level winds to such an extent that when the invasion of Europe comes on in 1944 and the director of the meteorological office suggests Sutcliffe ought to be the chief forecaster for the British because he's the best scientist we have, Bomber Harris, who was the vice chancellor for, or whatever they call them, for the air war in England, he said, there's no way I'm letting my best guy at number 3 group go and do some giant job for the complete Allied force. I need him for me. He's kind of selfish that way. So Sutcliffe was transferred instead to a totally military unit, Bentley Priory, in 1944. The rules were such that he had to come to work like this, dressed in a civilian suit and tie. Everybody else there was wearing brass. He was a fish out of water. He hated it, apparently. And he had something to do with the forecasts made for the invasion in 1944, but not really the primary role that if he'd had, maybe they would have had even better success than they did in the forecasting part of it. But he followed the army to France. He went from Bentley Priory to Granville in June of 44. When Paris fell in August, he went to Versailles. No jobs of any substance to be doing at either of these stops. He was living in a stable outside the palace grounds in Versailles. They didn't even care that he was there. But that's part of the way it goes, I guess, in big military operations. Finally, in the fall of 1944, he went to Brussels, and he was made the chief meteorological officer of the 2nd Tactical Air Force. And then he had a really substantial job to do. And he was there for the Battle of the Bulge. He was reunited with Godot at this time, so they were able to continue their investigations of flight level wind forecasting and so on. And that was a big deal for him. And then in March of 1945, they crossed into Germany, and he went to Mönchengladbach then. In fact, Sutcliffe was the chief forecaster for what was called Operation Vorticity in late March of 1945. And here's a picture of him. This is a staged photograph after the event. This is Coningham, the British chief of the Air Force, and a couple of other people, and there's Sutcliffe pretending to ponder the weather conditions on March 24th, 1945. It turns out they were really good, and it was very successful. The largest air and ground assault, I think, in the war, and it was Montgomery's idea, but Sutcliffe made the forecast for it. And so it was a big success. And then after that, he moved to Bad Ilsen in the week before the war was over and then stayed there for the whole year after the war. And he rebuilt the German weather service. The Allies were not going to make the same mistake in 1945 that they made in 1918. They were clearly going to win the war, but they were not going to punish the Germans. And how they resisted that, I really can't imagine. But they planned to not do that since 1942, before the tide had turned. Talk about the ultimate jinx. They were laying plans for how to rebuild German infrastructure in the whole country before they even knew if they'd win the war. And so they executed that plan beginning in mid-May 1945. And so Sutcliffe had a tremendous role, and the most important role, in rebuilding the German Weather Service after the war. And the German Weather Service now is as good as any around the world. And you can tip their hat to him for that. Finally, after all this, he was away now since, June of 1944. He's away from home since March of 1944, and now it's not until April of 1946, more than 2 years later, that he's finally demobilized and back in England. Because of the war, the Met Office had grown by a factor of 5 or 10 in terms of employees, and they needed to reorganize once they were done with the war. And so that left a lot of their senior scientists without too much obvious responsibility for a while they were trying to figure out where to place everybody. So what do you think Sutcliffe did? He went back and he thought about development again. I mean, the urgency of the war effort clouded his ability to stick on this problem. But finally, when it was over, he could go back home and say, let me just sit down and think about this again. So here's the basic ingredient. If you take the divergence of the curl of the acceleration, you might be able to say something about the vertical motion. But it occurred to him somewhere between 1939 and 1946 or 47 that instead of trying to figure out acceleration, let me think of another way to relate this. We know that the air rotates on all kinds of scales. You've seen dust devils. You've seen movies, hopefully only, of tornadoes. But you see satellite movies of giant cyclones. They're huge scale, 10 or 12 states. So it's not at all foreign to imagine the air rotating. And I've drawn a schematic of that. If the air is rotating like that, then on the periphery of that rotating vortex, there's going to be winds that I just highlighted, four of them here in green. The Coriolis Force tugs every motion in the northern hemisphere to the right at right angles, including those green arrows. So there's going to be winds that are dragging out from the center of that vortex. And what does that suddenly look like? Divergence. So there's a way to relate the rotation of air parcels and air and weather systems to the divergence that's so critical to figuring out whether the air is rising or sinking. And it's a variable called vorticity, the vortex nature of the flow. And so you can rewrite that expression for this expression right here, and it's just how are you rearranging the vorticity will tell you what kind of divergence field you have. So Sutcliffe says, let's apply this at two different levels in a single column of air and see what we get. I'm going to just go right through that. Turns out the difference in the divergence at the top of the column minus that at the bottom is forced by how you rearrange the vorticity by the vertical shear. The wind speed at the top minus the wind speed at the bottom gives you the shear in the column. Unbelievable. Here's how that works. Here's a large upper level vorticity maxima. So a big spinning parcel of air in the top green disk, less rapid rotation on the bottom green disk. They're both going to be pushed to the north by this shear. And by putting a purple arrow like this in this point, I'm saying that the push to the north is stronger at the top level than it is at the bottom. And the difference between the top level push and this is related to that. So if you have kind of weak pushing to the north on the low level one, then you're going to start to create a little vortex further north than the original position right there. Those winds that are in black are going to be tugged to the right, just like I showed you, and you're going to get a little bit of divergence at that level. But if you do this whole thing with greater vigor up here, well, what are you going to get? Stronger rotation at the top, stronger black arrow winds, stronger divergence, and if you have even greater divergence at the top of the column than you do at the bottom, the air in the middle has to rise. So rearranging the vorticity in the column is what tells you how the air rises. Oh my God, is this incredibly important. You could not figure out the acceleration of the wind with any sort of available observations. We still can't do that today. It's just too tricky. But it's not at all tricky to make reasonable estimates of the vorticity at one level, maybe the bottom of the column, and also at the top of the column. It's not difficult at all. And just by doing so, you can say why the air is rising. Opposite circumstances might make it sink. Unbelievable. Here's how it works. Look at this. This is the thickness field. So the shear wind will be parallel to these red lines. Here's vorticity from a certain day. Here's the advection of it. That's what we call it. It's getting more positive in the red and more negative in the blue. And then you can figure out, using his formula, what will be the vertical motion from the Sutcliffe formula. Green is rising, yellow is sinking. This is what you get from the highly sophisticated numerical weather prediction models today, without any of these assumptions. Okay? That is not just a facsimile, that's darn close to the real answer. And you're able to do this in 1947 with available observations. Is that a practical view in mind or what? That's practical. This is something that took decades to be able to do, and all it does is give you a little bit more refinement to that same view. This is unbelievable. It can't be overstated. How can my colleagues around the country not talk about Sutcliffe? Oh, it frustrates the hell out of me. This was instantly recognized as a major advance. He starts to win all kinds of prizes. Here's one, 1951. He's talking to C.G. Rossby here. This spurned the beginning of British numerical weather prediction. Rossby's effort with the United States was, let's make an even more horrible assumption about the atmosphere, and we won't even try to forecast where the air is rising or sinking. This didn't compute for Sutcliffe. He said, why would you even do that? If you don't know where the clouds and clear skies are going to be, what good is the forecast? So anyway, they had a very spirited, friendly relationship, but they argued all the time. He was elected to the Royal Society in March 1947. This is 57, not a small deal. First line forecaster ever to reach the holy precincts of the Royal Society. Every March, 25 people are voted in, and colleges around the country are looking to see if any of their alumni made it. The registrar at Leeds found out that Sutcliffe made it. Wrote him a nice letter saying, congratulations. I should have kept this written up here, but I'll try and read it from the original, from the archives. This is Sutcliffe's response. Listen to the beautiful language here. Dear Sir Charles, I am so glad that my election to the Royal Society has been noticed with pleasure at my university, and that you should have been moved to write me personally about it. Some of us cut away from our universities as we do from our parents, with gratitude unspoken, and never find the right occasion to express the warmth of our regard. Of course, we owe everything to them, and I would like through you to express a deep gratitude to Leeds after 30 years of enjoying the fruits of the trees they have planted. With many thanks, yours sincerely, R. Sutcliffe. It's like Abraham Lincoln prose, right? Isn't it? Unbelievable. He's made a most honorable Order of the Bath, June 1961. This is the fourth order of British chivalry, I think. It's one step below the first of knighthood. There's the award. I saw it at Ellen's house. There's Ellen and her husband, Dick, who are good friends of mine now. And outside Buckingham Palace, and Reggie and Evelyn. She's looking bored. How many times do we have to do this, Reg? This is my fourth time. The royal family comes to the Met Office. They had a new building in Bracknell built and opened in 1962. So here's Sutcliffe talking to Prince Philip about the 500 millibar map, maybe, or something. He meets the Queen again, because she bestowed the Order of the Bath, June 25th, 1962. He gets the WMO prize in 1963, and I can't tell you more about this, but I'll just read the inscription. In recognition of his outstanding contributions to dynamical meteorology, some of which we've talked about, his furtherance of international cooperation in the science of the atmosphere, and his leadership in research. Sutcliffe was devoted to bringing countries, third world countries, into the World Meteorological Organization, not as a messianic mission, but in recognition of the fact that we can't make good forecasts of the weather unless all countries are involved in this. This is huge. 21st Pearson lecture at his school again, March 6, 1965. There's the ticket to get in, and I mentioned it to a couple of people. The title of the lecture, Predicting and Controlling the Weather, 1965. This was, I mentioned to some of you, the initial impetus for numerical weather prediction as a goal was to, of course we have to know something about how to predict it, but what we really want to do is control the weather. Imagine that. We gave up on that a long time ago. Thank God. I visited his school 50 years to the day at that lecture. And there's Pearson on back in Cleckheaton from his retirement in Bermuda, watching proudly as Sutcliffe talks about the weather. Sutcliffe quit the Met Office in 1965. He didn't want to work for B.J. Mason, who was going to be the new director. B.J. Mason is my PhD advisor's advisor at Imperial College. So I'm the intellectual grandson of the guy who Sutcliffe couldn't stand working for. So quite interesting. So and I got to give a talk like this at the Sutcliffe Lecture Theater. See that? And there's a picture from the cover of the book. He wrote a popular book on weather and climate in 1966. You can still find it. I recommend reading it. They spelled his name wrong on the cover. And then they wrote him a letter and said, sorry we did that, but none of those books got out, except, I guess, the one to his daughter, right? And they, at the time of apologizing, they said, would you be interested in writing a short introductory text in meteorology? And he said, I'm too busy, I can't do it. Too bad. Imagine having somebody who wrote that letter to the registrar writing a book on this science again. That would have been great. Finally, here's his family and some of the people I've met in my journey. Here's Dick and Ellen today. This is actually Christmas 2014. Their daughter Lucy, her husband Nick, Sam and Rory, and then their daughter Harriet and her husband Dave. I was welcomed with open arms. I didn't know what to expect. When I made contact with them, I thought, they're going to just think this Yank is nuts. What's he doing? But totally wrong. They did their homework. They had stuff on tables. And so did Jenny and Jacques in France. Same exact thing. Just amazing. It was great. I visited the Sutcliffe gravesite at St. Mary the Virgin in Evelyn's hometown, Pentry Halkin. And the inscription on the gravestone is the first line from Shakespeare's Sonnet 33, "Full morning, many a glorious morning have I seen." So I've gone a little bit over, but I've only told you a few of the stories. You can find the rest in my book. I talked to a bookseller across the street. He's eager to order them for you if you want to get one. And if you don't want to do it there, Mystery to Me in Madison. I have an in there. You can get them online. I'll sign it for you. So, and it won't cost you a thing. So
Thank you.
I'd be really happy to do that for you. But thank you so much again for inviting me up. I hope you've enjoyed it, and I'll take any questions.